Hey guys! Today we're going to do a brief introduction of waves. This really should just be a review because you should have learned about waves already either in your high school career or during 7th and 8th grade. In high school, you should have seen it in physical science class briefly. You also should have seen it possibly in human phys, talking about optics or hearing when it comes to the body and how they interact or interpret the waves. First, we're going to take a look at the individual parts of a wave and just characteristics of a wave in general that you should already know, but again, we're just going to review. So the first thing, there are two types of waves that we will be discussing. The first type is mechanical. These waves require a medium to move through. That means they have to have air or water or a rope or something that they have to travel through. This could be like sound waves. This could be like water waves or the waves on a slinky or a trampoline. The second type of wave is an electromagnetic wave. These waves do not require a medium to move, such as light rays. We get light from the sun even though there are no particles in space for the light to travel through. Radio waves are another example. We are able to talk to people on spacecrafts and space shuttles without actually having air particles between us because of radio waves. And X-rays. In this unit, we will specifically be focusing on mechanical waves only. Alright guys, so the first type of wave that we're going to talk about are transverse waves. And transverse waves occur when the medium moves perpendicular to the direction of the motion of the wave. So I'm going to go ahead and press this little video so we can see how this works. So the wave is actually moving from the left-hand side to the right-hand side. It's traveling in that direction. Just like on this picture above, the wave starts here and ends here. But the individual particles in the wave are actually just moving up and down. So in order to create a crest, it moves to the very, very top, and then it goes all the way to the very, very bottom, and it just keeps going up and down in that direction. So since the wave moves left to right, and the particles move up and down, this is considered perpendicular, and that makes this a transverse wave. So what I want to do is define these words over here, and then label them on the screen. So the first word is a crest, and a crest is the topmost part of the wave, and that is here. So I'm going to write crest. Notice there are 1, 2, 3, 4 crests on that wave. The second word is a trough, and that is the lowermost part of the wave. And there's one here. And again, there's 1, 2, 3, 4 troughs on that page. The next word is amplitude. And the amplitude is from the resting position to the top of the crest, or from the resting position to the bottom of a trough. It should be the same distance, so it shouldn't matter which one you measure as long as you measure one. Remember, it's from the center or the rest position out. It does not include a crest and a trough, just one or the other. Now, wavelength is going to be the most difficult thing to look at. So I'm going to draw a wavelength here. It goes from this location to this location. It is the crest to crest because it gives us half a crest, a full trough, and another half a crest. Or it's trough to trough because again gives us half a trough, a full crest, and another half a trough, which is a total of one wavelength. The next one can be on the rest position, one crest, one trough. This could also be considered wavelength. And wavelength is labeled in this funny Greek unit. It's actually a lambda, so in our calculations and in our equations, you're going to see this unit, not a W. So wavelength is the length of space it takes for one crest and one trough to occur. And the last word is the rest position. The rest position is this dotted line down the center, which is where the wave would be if no energy was moving through it. So the first type of wave is a transverse wave. It's the type of wave we're going to be most used to, and it's the type of wave that we're going to be using most often. The next type of wave is a longitudinal wave. So this is when the medium moves in the same direction as the wave. This diagram has this little video underneath it to show us what happens. And if you can picture one dot, so notice this one right at the very, very bottom, it moves right and then left, and then right and then left. The actual wave moves in that same direction also. So the particles move in the same direction as the wave. These specifically are like sound waves. Sound waves, the particles in the air vibrate left to right or forwards and backwards in order to transfer that energy through the particles of the air to your ears. So there's only 3 things we're going to define on this one, since we're not going to use it as much. Compression is the area of high density of molecules. So on this drawing, this is the area of compression. Rarefaction is an area of low density of molecules. So that would be here, right in the center. And just like on the last slide, a wavelength is a crest to crest or a trough to trough. It has to include 1 full compression and 1 full rarefaction. So you can measure that from center of compression to center of compression, or center of rarefaction to center of rarefaction, or the very, very beginning of a compression to the very, very beginning of the next compression. Any of those count. So transverse waves and longitudinal waves. They actually relate to each other. Sound waves can be treated as transverse waves, and they can actually kind of convert them back and forth to make them a little bit easier to use. So this diagram shows us that every location that has a compression is the same as having a crest. Those 2 things are synonyms almost. Every place that we have a rarefaction, we have a trough. Those 2 things are almost synonyms. Okay, so compression and rarefactions can be translated to being crests and troughs, like in transverse waves that we're used to. So the last thing we're going to do on this set of notes is draw a wave. I'm giving you 2 specifications that you have to follow for this wave. So the first thing I want to do is look at this diagram. Notice I have a slightly heavier black line across the middle of this graph. That's supposed to indicate our rest position. So my brain likes it when I have a full crest and a full trough in 1 wavelength. When I worry about half crests, full troughs, half crests, or half troughs, full crests, half troughs, it tends to get me confused. So I'm going to start right here, and I'm going to count. I need a full crest and a full trough in 4 blocks. So 1, 2, 3, 4. My entire wave has to fit here. So if I need a full crest and a full trough, that means that I should have a crest in half of that distance. So 1, 2. Now before I draw any waves, I want to take into consideration this amplitude of 3. So what I'm going to do is I'm going to count up 1, 2, 3, and I'm going to draw a dotted line just to remind myself not to go past that position. So I went up 3, dotted line, down 3, dotted line. Now I'm going to create my wave. I need a full crest in the first 2 blocks and a full trough in the second 2 blocks. So I'm going to do my peak at about the 1 block and my lowest trough at about the 3 blocks. Okay, so it's not necessarily pretty, but it does work. This is 1 wavelength of that wave. Now if I were to continue it throughout, I'm just going to put dots every 2 because I'm going to remember crest in 2, trough in 2, crest in 2. Okay, so that is 1 wave with a wavelength of 4 and an amplitude of 3. This will be the first thing that we end up practicing with, is just drawing waves based on certain characteristics. So I'll see you tomorrow and we can practice this in class.